Are you currently in the design process trying to decide between two different clock sources? Do you need to know how to accurately characterize those clock sources to make sure you choose the best clock or oscillator for your design? Hi, welcome to the lab. My name's Chris Higgins, and in the last video, we looked at the 53100A phase noise test set, how to set it up, how to use it. But today, we're going to look more in depth on what those measurements actually mean and how we can characterize our oscillators the most effectively. Now, this is by no means a full explanation of phase noise, but let's do a quick rundown so we know what we're looking at when we switch to the GUI. So when you look at a clock signal, you'll get a nice square wave like so. And you want your square wave to always be on time all the time. If you get a 10 megahertz clock, you want it to be oscillating at 10 megahertz without a doubt. But that doesn't always happen in the real world. Sometimes your falling edge will happen a little late or a little early, or your rising edge could be way off. And that's going to create some conflicts, especially when you're working with digital electronics. You need more margin, or when you're communicating serially. But this is only half the story. This is in the time domain. When we look at how the power of this signal actually bleeds out, you'll see a distribution like so. Most of the time it'll be on time, but sometimes when you're a little late or a little early, you'll start to see this distribution. Let's zoom in on this real quick in the frequency domain. So let's draw this distribution here. We've got frequency in our x-axis and power in our y-axis. Now, if you were working with a strict, say, 10 megahertz oscillator, you're going to see this one point and all your power is right there at 10 megahertz. But due to this jitter, that doesn't always happen. You'll get some bleed out into other frequencies. So what you can do is you can take a bandwidth like so, and you can measure the power of your signal in that bandwidth. And when you do this at a bunch of different offsets at different hertzes, you sweep all the way across, and you measure the power, and you'll do that in relation to the carrier, you'll get a nice metric in dBc per hertz. And when you calculate that power at all of your different offsets, you'll be able to get a phase noise measurement, which is what our 53100 does. Now let's switch over to TimeLab and look at a couple different oscillators, and let's do some sightseeing on those plots. Now, on the top in the blue here, we have our Microchip CSAC, our chip scale atomic clock, and right below it is our low noise version, or our LN CSAC. And the two parts of these plots are the thick line and the shaded area underneath. And I mentioned in our last video that the shaded area underneath is the phase noise floor of the instrument. And this is heavily determined by the reference you're using. So on our internal reference version, we have 200 megahertz OCXOs that we use for our references. But if your setup had one OCXO or one other atomic clock, you may need to measure longer or in a more stable environment to bring that shaded area down. And you want about a 10 dB difference between your line and the shaded area. But looking at the trace itself, you'll see that out here past around 100 kilohertz, maybe 10 kilohertz, you'll start to hit the noise floor of whatever you're measuring. So this could be things like thermal noise or other random noise effects in your system. But when you get closer around the 1 hertz mark or the 10 hertz mark, you'll start to see things that are more characteristic of the device you're trying to measure. Now, in some devices, like in quartz oscillators, you'll see some of the spurs that are indicative of environmental conditions. One really popular one that you'll see is around 60 hertz and 120 hertz. And if you're in the US, that's what our power grid is based off of. So you'll see the frequency from your power bleed into your measurement. But if you get really close to the carrier, say around this 10 hertz bandwidth, you'll start to see things that are present in the system. Say this spur here at 7 hertz is actually intrinsic noise to our device under test. So maybe you want to mark that, come back to it later, use some other analysis techniques to find out where these frequencies in your system are popping up. Another really powerful tool that this view gives you is the ability to measure jitter. If you work in the time domain, you'll work with jitter a lot more than phase noise. But let me show you how to pull that up here. So you'll go to Legend, you'll select, and then you'll go down here to this RMS time jitter. This will give you a bandwidth with these blue cursors here, and it will integrate that and give you the RMS jitter down here in the Legend. And the way you change that is you hold Control, and you left click for the left bound, and you right click for the right bound. So why not take these measurements with an oscilloscope or say a spectrum analyzer? Why should we use a phase noise test set like the 53100? Well, an oscilloscope really works well in the time domain. Some oscilloscopes, some higher end ones, might be able to do a fast Fourier transform, get you some frequency data, or a spectrum analyzer might be built for frequency, but a lot of these phase noise features are kind of crammed into those devices. A specifically made for phase noise measurement test set, such as the 53100, will allow you to make these measurements much, much faster than if you needed to do iteration upon iteration in, say, a spectrum analyzer. If you really want to do super fast measurements, the 53100 has two different FFT masks that are used, a coarse one and a fine one. The coarse one might be useful in things like ATE or test software when you're really trying to make measurements fast that are still accurate. The fine FFT mask might be more useful in an engineering application where you're trying to find spurs, see where the noise sources in your device are coming from, and this affects your measurement time. So on a coarse FFT mask, you'll be able to hit a hertz in about 5 to 10 minutes. If you're using the fine FFT mask, really looking for spurs, you're going to want to wait closer to 30 minutes to get a full measurement. So to my point here, let's look at TimeLab real quick again. What I have in the blue and pink are the same exact low noise CSAC, but I took one with the coarse FFT mask and one with the fine FFT mask. Now in the blue here, we have our fine FFT mask, and you can see that we're able to differentiate between spurs. Our resolution is a lot higher. You'll see a greater accuracy in the power of these noise frequencies. But if you look at the pink, we got a lot closer to our carrier. The close-in phase noise was measured a lot faster. Both of these were only run for 15 minutes. So it's a trade-off between accuracy and time. If you're looking to make really quick measurements, maybe you just need the coarse FFT mask. But if you switch over to the fine ones, say in an engineering setting when you're trying to do analyses on these oscillators, you might want to take the time, get a good long measurement, and get that resolution that you're looking for. How do I apply this? How do I take this into the evaluation process? I've measured a couple different oscillators and I'm trying to determine which one I want to go with. Well, let's look at phase noise and why that might be important. So here we have a scenario where I am trying to receive a signal. Let's say this is our signal. But let's say a couple hertz over, we have a very strong signal looking like this, but we're trying to measure this one right here. Now, where phase noise comes in is when you're trying to receive this signal and you're multiplying down to a more workable frequency. That oscillator that you're using matters, and the phase noise of it is going to impact your measurement. So let's say we're working with a really noisy, low-end oscillator, and the noise that your receiver picks up goes like this. What you'll actually do is you'll see that the noise from this signal will completely mask what you're trying to measure, leading to unreliable communications or missing transmissions. So in this situation, phase noise is essential, and measuring using the 53100 will give you confidence that you're choosing the right oscillator for your design. Now let's take a look at our Adev, or Allen deviation plot, that the 53100 also helps us acquire. So here we have, same as before, our CSAC versus our low noise CSAC, and this gives you a sense of stability in your oscillator. Things like quartz, or OCXOs, they'll have really good short-term stability, but they'll start to drift in the long term. The things that we're looking at today are atomic clocks. So their long-term stability is going to be much, much, much higher than, say, a quartz. But let's look at that real quick here. So on the top, we have our CSAC and our low-noise CSAC on the bottom. And you can see that they're about an order of magnitude apart when it comes to measuring the stability at a second. And this really shows you how much will my frequency change in the matter of every second. From second to second, how much will it change? So moving past the short-term stability and looking farther into the future, around 30 seconds, 60 seconds, 100 seconds, in that range, you'll see that these plots actually start to line up. And we're able to compare the CSAC and LN CSAC to see where they start to line up in that long-term stability range by putting both of the plots on top of each other like this. But what I do want to pull up is one of our really stable clocks, the rubidium clocks. So we'll open our .tim file, and we'll look at our MAC, our miniature atomic clock. And this uses rubidium instead of cesium, slightly different technology, but you can see the comparison between short-term and long-term stability in these different styles of clocks. So in terms of short-term stability, you can see that the LN CSAC blows both of these out of the water, but in terms of long-term stability, you want the most accurate clock after 110,000 seconds. You might want to go with a rubidium. So that's all for today. As always, if you want to learn more about this test set or look at our app notes, there'll be links in the description. Thanks for watching, and I'll see you next time in the lab.